Hello, so today we are going to do this problem called build a matrix with conditions. So this is part of Leetcode contest 308, this week's contest. So let's get started. So the problem says we get a positive integer k, and we get two integer arrays, row conditions and column conditions. And row conditions has a size n, column condition has size m. And what they contain basically is two numbers for rows above and below, and for a column left and right. What these represent is basically rows conditions for the numbers. We'll explain how to interpret these in a second. And these two arrays contain integers from 1 to k. And what we want to do with these is build a k by k matrix that contains each number from 1 to k exactly once, and all the other cells are 0. And for these conditions, what we want is for above, the value in above should appear in a row that is strictly above the row at which the number in below appears, right? And left, it should appear in a column that is strictly to the left of the column for right. These are numbers, by the way, from 1 to k, right, that we want to place in this matrix, in this k by k matrix. And so the goal is to return any matrix that satisfies all these conditions here. If we take a look at an example, that will be, I think, more clear. So k equal to 3, which means we have 1, 2, 3 numbers that we need to place. And row condition says that 1 needs to be above 2, because this, just by being in this position, that's the above position in the condition here, right? So 1 needs to be above 2, 3 needs to be above 2 as well. Okay, so from this you can deduct that 3 needs to be the top one, because it needs to be above 2. 3 needs to be above 2 and 1 needs to be above 2. So either 3 or 1 need to be the top row, and then 2 has to be the bottom row. And so we can choose to place 3 in the top row, 1 in the second row, and 2 in the third row. That way we have 1 above 2, 3 above 2, and all these conditions are valid. For column conditions, we need 2 to be to the left of 1, and we need 3 to be to the left of 2. So we can place 1 to the far right, that way left is to the left of it, 2 is to the left of it, and 3 as well as to the left of it, because both needs to be to the left of 1, right? And so these conditions are also now satisfied in this matrix. We don't need, there may be multiple solutions, so we need to return just any matrix that has these conditions. The other thing is that if we can't find the placement, a valid placement, we can return an empty list. Because here we have 1 needs to be above 2, right? 2 needs to be above 3, but then 3 needs to be above 1. So you can see this is contradictory. It's not possible. So that's why we return empty list if it's not possible. Yeah, so that's pretty much the problem. Now let's see how we can solve it. Okay, so let's see how we can solve this. So let's take the first example. So we have the row conditions, let's call them rows conditions, like this. So we have 1 above 2, and then we have 3 above 2. And then for the columns condition, we have 2 to the left of 1, and then 3 to the left of 2. So you can see here, first, we can first separate these, because this one only takes care of telling us where is the row position, right? Here, it only tells us where is the row position, and here it only tells us where is the column position. So we can treat these two problems independently. So that's the first thing. The second thing is that, well, if we take a look just at the row here, 1 above 2, so we can treat this as some sort of graph representation. So 1 is above 2, so let's make 1 have an edge, a directed edge, toward 2, sort of a graph. And then 3 is above 2, so also an edge like this. Okay. So if we do it like this, so right now we'll just focus on rows order. So if we do it like this, let's say maybe in another example, maybe we have, let's say 4 above 3, for example, right? Let's say this is a larger, maybe here we have 4 to the left of 2, or something like that. Just to give you an idea. So here, this means that 4 needs to have an edge to 3, okay? So you can see here, if we do this, then what we want 1 to be above 2, we want 4 to be above 3, and 3 to be above 2, right? And so with this, if we do sort of a topological sort, topological sort basically means that first we start with those that don't have any dependencies, right? So they can be at the top. And so first, 1 doesn't have any dependency, so we can put it at the top here. So this would be 1, 2, 3, 4. This would be 4 by 4 matrix. And then just for the row, we know 1 needs to be in the top row. So let's do it differently. So 1, top row. So we can have some sort of order that we generate. So we have 1 top row. And then 4 also has no dependencies. Basically no incoming edge to it, which in graph terms, this just means in degree. So when the in degree is 0, that means we can add it. And so now we add 4, because 4 can be to the top. And now once we add 4, we delete the edge, right? Because we delete this in degree. So now it has in degree 0. First, this has in degree 0, this has in degree 0. This one had 1, and now once we take care of 4, it has in degree 0. 2 had in degree 2, right? And now we have 3 that has in degree 0, so we can add 3 as the... This basically means 1 needs to be into the top row, 4 in the second row, 3 in the third row. Basically, this is the indices are the row order, so let's call this row order. And then once we now remove 3 and has in degree 0, we can add it. And now we take care of this edge. Now the in degree is reduced by 1 because there is no more, this edge is no longer there. Let's say we process also this one, right? And now the in degree is 0. And now we take care of 2. And we put 2 here, right? So 2 can be in the last row. So you get the idea. This is just doing topological sort. You can read up on it if you want, but this is topological sort. So in a nutshell, what we do is we use the row conditions here to construct a graph with dependencies 1 an edge to 2, 3 an edge to 2, 4 an edge to 3. And then we use that graph to determine what are the first ones that don't have any dependencies. So in degree 0, those are the top rows. And then as we visit a node and take care of it, we remove we take care of its neighbors, right? And for each of its neighbors, we reduce the in degree by 1 because we took care of the first one, and so potentially it could be the next one. And then we keep doing that. We keep visiting the neighbors. We keep visiting the neighbors, and every time we take care of one of them and add it to the row order, we reduce the in degree of all of its neighbors, and we visit its neighbors, and we check if their in degree is 0, we add them to the row order. So this is just normal topological sort. It can be done this way with in degree, and here we can use BFS, or we could also use DFS and kind of add the node in post, right? So we can also use DFS if we want. I'll start with the BFS solution, and we can go from there. So this is just for the rows, but this solution is applicable to the columns as well. It's almost the exact same thing, except what we will get is the column order instead of the row order. So we do 2 has an edge to 1, 3 has an edge to 2, 4 has an edge to 2, and we'll do topological sort again, and we'll find the column order. Okay, so now, after doing this step, we should have both row order and column order. That tells us which row is the top, like from the top to the bottom, and here tells us from the left to the right. Now the problem becomes how can we reconstruct the matrix, right? And that should be easy, basically. So we can just create first initially a matrix with just 0 values, right? and just look up the row order and the column order to see where we are, right? So I'll take the example we have, just to make this quicker, I'll take the example we have with just 3 by 3. So where our row conditions are 1, 2, 3, 2, and then our column conditions are 2, 1, 3, 2, right? And so what is the row order we get? So 1, 2, and then 3, 2. So this is for the row. So the row order becomes 1 or 3. We can start here or here. That doesn't matter. 1, 2, right? And then for the column order, we have 2 edge to 1, and then 3 edge to 2. And so this would tell us that the column order is 3, 2, 1. So these are the indices for the row and column. So we can just take a look at this. Where do we place 1? Let's say, where do we place 1? So we know the row for 1 is 1, and the column for 1 is 2, right? So this tells us we need to place, let me just add the indices here. So this is 0, 1, 2, 0, 1, 2. So this tells us basically we need to place 1 here, right? And now we check the place for 2. So the row for 2 is 2, right? And then the column for 2 is 1. So this tells us we need to place 2 into 1, which is here. So this here is 2. And now let's check the place for 3. So the place for 3 is 0, and then, sorry about that, 0 and then 0, right? So this tells us that 3 needs to be here. And that's a matrix that we can return. So we can just look at the indices, and for that we can just use the row order that index of the number, and column order that index to find it. Okay. So this would be for I, yeah, for the number that we want to place, and this will give us the index x and y, and we can just place in that coordinate in the matrix, right? Yeah, so that's pretty much it. Let's just recap. So for each of these conditions, we create a graph and use topological sort to find the order, the row order and the column order. And from there, we create a matrix with empty, with just 0 values. And then we find the place for each value and assign it, right? So that's the main thing. Now, one thing is missing now is that what if it's not possible, right? When it's not possible, the problem says we need to return an empty list, right? So in that case, how do we do that? How do we detect that? It's simple. If we, with topological sort, right? If we weren't able to find the order for all of them, right? That means there is no solution. So we can just do a check at the end of our topological source to make sure that the row order, we do the same for the column order to make sure that the length of this is equal to all numbers, and the numbers we have are just k numbers. So if this is equal to k, right, that means we are good. So we can return row order. Otherwise, it's empty because there is, we weren't able to find everything. We need to find the order for all numbers. And in the result, if either row or column order is empty, you can just return empty list, because that means we encountered a problem and we weren't able to place all the numbers, right? Yeah, so that's pretty much it. Now let's get started and code this up. Okay, so let's code this solution. So the first thing we need to do is just get the row order, right? Let's call it get order, because we'll generalize it for all of them. And then from this would be, we'll pass the row conditions, right? And then we want to get the column order, and here we'll pass the column conditions. And now we need to define the get order for some array. Let's call it A. And we'll do BFS here in topological sort, pretty much. And so here, how do we implement it? So we need a queue for our DFS. You could use DFS if you want, but I'm just going to do BFS here. And we need a visited set. And we need a graph that will reconstruct from row conditions here. And so collections, for each node will have all of its neighbors. And this is directed graph, by the way. And now to get the graph, we'll just go through the row conditions. Now, one thing to remember is that the rows conditions are like 1, 2, and then 3, 2. So they are indices starting from 1. I want the graph to have indices starting from 0, right? So basically this would mean this is actually 0, 1, and 2, 1. Yeah. And so to do that, that means the node is actually I minus 1, and its neighbor is j, but if we convert it, it's j minus 1. And now we need the in degree, which means basically how many incoming edges to the node. And here, this row basically means that we have a row I to j, right? Because in the row condition, this means I is above j, so we have the row like this, which means the in degree of j needs to be increased by 1 because there is this one coming from I. Yeah, in our problem here, this is I minus 1, j minus 1, just to make this super clear. Yeah, just converting these indices. And so this would mean the in degree here, for j minus 1, we need to add 1. Now we need to construct, we need to initialize this in degree map, right? So let's define it maybe here in degree that append. Let's just use a map that is defaults to 0 for the int value. Okay, so now that we do that, we need to initialize our queue with all the nodes that have in degree 0. That's what we did earlier when we had, in the problem, we had 1 to 2 and 3 to 2. And each of these didn't have any incoming edges, so we need to start our queue with 1 and 3, right? So that's what we'll do here. So we'll go through all the i's, range of k, because we have, we are starting from 0, so this would be, let's say k equal to 3. This would be 0, 1, 2, right? Which is equivalent to 1, 2, 3 that we did in the overview. And so here we will check if the in degree that we, after constructing the graph of I is equal to 0, then we add it to the queue. And let's mark it as visited because we added it to the queue already. Yeah, let's add it as visited here. You can choose also to add it as visited in the traversal. Both should work fine. Okay, so now we'll do our traversal, and we'll just have the order array that we'll store here. And while we have something in the queue, we'll first pop it. And then we will add order append current value. And now we'll go through the neighbors for that current value. So we add it because we just visited it, right? The first one we visit is because its in degree is 0, and so it's the first one in the order, right? And now since we visited the node, like we said in the overview, we need to decrement the in degree of the neighbor, right? Because this here means basically that we have an edge like this, current to neighbor. And since we visited neighbor, we need to decrease the in degree of neighbor. We visited current, so we need to reduce the in degree of neighbor. Now, if it becomes 0 as a result, and we haven't visited it yet, then we can visit it. And visiting it just means adding it to the queue so that on the next loop we pop it off. So append that, and then we need to mark it as visited as well, right? So that we don't visit it again from another edge. And now that we are done here, we need to return order. We just need to do one check if it's not possible, which I said if we weren't able to get the order of all the elements from 0 to k minus 1, right? This is similar to 1 to k, just like we are changing the numberings to start from 0. But overall, the length should be k. which means we found a place for each number. And so here, if only we found a place for each number. If we didn't, that means let's return empty list. And this should work for both row and column. So I need to change this to A so that whatever is passed here is what we use. And now that we have the the order for both, we can check if any of them was empty. That means we weren't able to find a place for all the elements. So if row order, not row order, this just means it's empty, or not column order, we need to return empty. And now we place in matrix, place elements in matrix using the order arrays. So to do that, we'll need to create our empty matrix first. And so it just starts with 0. It's k by k matrix. So just range of k, and this is for range of k. And what we need here is to go through every number. Remember here we can stay from 0 to k because what we started in the row order is actually from 0 to k minus 1. And so here we get the I position and the j positions. Let's call them I. This would be a row order, the index of the element I. Maybe let's call this x just to make this easier. Okay, and then we need the column position. So now we get the place for the value x, and we place it in our result matrix. Right, pretty straightforward here. We place x, right, plus 1 though, because this is from 0 to k minus 1, so we need to convert it back so we need to convert it back here to 1, 2, 3, 4 instead of 0, 1, 2. And then at the end we just return that result matrix, and that should be it. So let's run this. Looks like there is a small problem here. We used row order in column order. Let's see. Okay, yeah, so there are 2 errors here. First, here we need visited, so that also if there is a cycle and we visited a node multiple times as a result, we need to mark that here. And if there is less, we need to know as well, right? We need to return empty because that means we didn't find the order for all the elements. And the second thing is that here we want the integer to be equal to 0. We don't want it to be bigger than 0 because then that means we can't process that node yet because it's not it's not the next in the topological sort order, right? Okay, so let's try this now. And let's submit. By the way, this is a valid still matrix order, not the exact same one, because we may have different types of different instances, but both are valid solutions, right? And this passes test cases. Yeah, so that's pretty much it, I think, for this problem. Thanks for watching, and see you on the next one. Bye.